So I'm very glad to have the opportunity today to present you some extensions based on the joint modeling of repeated markers and time to events in neurodegenerative diseases. So before I go into the details of those specific models, I wanted to remind you about the joint model principle. I don't know if all of you are very familiar with this methodology. So when we study the progression of chronic diseases, for example, cancer or Alzheimer's disease, or etc., we study that through the repeated measures of biomarkers. So for cancer, that can be the tumor size or the PSA in prostate cancer. And we also have the clinical progression, which is usually a time to event. And those two types of processes are very interrelated. And so we need to analyze them simultaneously. And that's the principle of the joint models, to analyze those processes simultaneously. Why? Well, because that will help us to address different types of research questions. That can be to assess how the biomarker will impact the risk of event, so the association of the marker with the event, or to describe the biomarker while taking into account the fact that it may be stopped by the clinical progression. So we have here a problem of informative dropout. Or we can be interested in predicting at an individual level the risk of progression using the biomarker information we have collected so far. And basically, we can just be interested in exploring the association we have between different processes of progression. Whatever the question, the structure or the principle of a joint model is always the same. We will have the repeated biomarker. So here, this is an example with the log PSA, so the biomarker that is used to look at the progression, to monitor the progression of prostate cancer after a treatment. So here, this is the end of treatment, and we have repeated measures of PSA. And we have a time to event. So here, that's the clinical recurrence of prostate cancer. The idea is that to take into account the correlation we have between those two processes, we will assume that we have a latent structure that will capture entirely the correlation we have. So we have a conditional independence of the repeated biomarkers and the time to event given a latent structure. Usually, this latent structure will correspond to some random effects. When we model the repeated biomarker measures, we use a mixed model based on individual random effects. And the main type of joint model is to assume that we can use those random effects to make the link with the time to event. That helps us to quantify the effect of the biomarker on the risk of event. So if we want to formalize that a little bit, so the latent structure are a random effect, so that's latent variables, which are usually have a Gaussian and a multivariate normal distribution. And then we will consider a model for the repeated biomarker given this latent structure, and the same for the time to event. For the biomarker, my notations are that Y is the biomarker for subject I at time Tij, where J is the repeated occasion. And when I look at a biomarker, an observed biomarker, I will make a distinction between the observation and the true signal that is underlying this observation. So the true biomarker level with a star here. And basically, my observation is my true level plus an error. And then in a linear mixed model, what I do is that I will describe this true biomarker level using both some characteristics at the population level. So that's some covariates related to time, which will look at the shape of my biomarker over time and fixed effect. And to take into account some individual differences, I will use my random effect. So to take into account a departure, an individual departure from this mean trajectory. So my random effects are here to describe the correlation I have between my repeated measures of each individual. And then I will also have a model for the time to event, so a proportional hazard model. Usually, you could have something else if you want, where the instantaneous risk of event will be defined according to this random effect. So basically, with a baseline risk function, and then a linear predictor with covariates, classical covariates, and a function here of my biomarker. So a function of z, bi, x, and beta. And that will take into account how my biomarker is associated with my event. So that can be through the current true level, for example, y star of t, or that could be the current slope, or etc., etc. And I have a eta parameter which will quantify this association. So I will be able to really quantify how my biomarker is associated with my time to event. This is this has become standard, and with many packages in R that can be used to estimate such model. But this is not the only way to define a joint model. We could think of another way to do that. Usually, if we suspect an association between the repeated marker and the time to event, it might be because our population is made of subgroups that share the same type of repeated biomarker trajectory and the same type of event. So basically, my latent structure could be subgroups, latent classes, and would explain that my population is heterogeneous, and that's why I would have this type of association. So this defines the joint latent class models, which are more a descriptive approach to look at multivariate processes. So the idea here is that the latent structure now is not a continuous random variable, but a discrete latent variable with Ci, my latent variable, which so Ci equal G if my subject I belongs to latent class G, so to group G. I will describe this distribution using the probability of each latent class, and then similarly as what I did just earlier, I can look and define the trajectory of my repeated biomarker given my latent structure. So now, given my latent class. So this is also a linear mixed model, but now the parameters at the population level and the distribution of my random effects can be different from one latent class to the other. And so I will have different profiles of trajectory. Then I can also look at the time to event given this latent class structure. And this is very easy. I just need to define a proportional hazard model where, for example, my baseline risk function is different in each latent class. We have developed this methodology in LCMM in R. So just to give you an idea of the kind of results we can obtain. So in my example with the log PSA observed after the end of a treatment in a prostate cancer patient, we found 4 different groups of trajectories, so four latent classes associated with different mean profiles of trajectory of PSA and associated also with different risks of recurrence. Whatever the type of joint model that you assume, the principle of estimation will be the same. So I will focus here on the maximum likelihood framework, but you could also think of Bayesian approaches if you want. And the principle is really the same. The idea will be to integrate over the latent structure by taking into account the fact that when I defined the models, I told you that we have a conditional independence between the repeated biomarker and the time to event given the latent structure. So when I define my likelihood, my individual contribution to the likelihood in a joint latent class model, because my latent structure is discrete, I will have a sum over the different latent classes, and then the conditional independence will separate the conditional density of the biomarker given the latent class from the conditional density of the time to event given the latent class, and then the probability of the latent class. In a shared random effect model, my latent structure is now continuous, the random effect. So I replace the sum by an integral. And then I also have this conditional independence, the conditional density of the biomarker, but now given the random effects, separated from the conditional density of the time to event given the random effects, and then the density of my random effects. So exactly the same way of estimating the model. But from a practical point of view, the numerical complexities, and both have some, are very different. In a joint latent class model, I will usually, when I want to estimate this type of model, I will have to deal with a very usual problem in mixture models, which is the multimodality. So I can have multiple maxima of my likelihood, and I will have to deal with that. And I also have to take into account the fact that I don't know the number of latent class G, but I need usually to define it in my estimation. So basically, I need to estimate this model for a given number of latent class G, even if I don't know it. In a shared random effect model, the problem is a little bit different. The problem is linked to this integral. This integral is not a one-dimension integral. It's an integral that of dimension the number of random effects. And usually you don't have only one random effect to describe the repeated measures of a biomarker, but 2, 3, or 4. So you have a numerical integral that is not very easy to compute, and it has to be done numerically. And so you might have some problems with this numerical integral with a lot of inaccuracy in that goes to problems of estimation of these models. Okay. So the methodology of the joint model has been developed from the years 2000 to study one biomarker and one time to event. But the problem is that when you study some diseases, well, you don't have only one time to event, but you can have a more complex event history. And so you might need to extend this methodology to account for the specificity of your event history. For example, you might have competing risks. So, for example, different types of recurrence in prostate cancer, or you might also have some different states of the disease, so multi-state data. Well, this is not so complicated to extend the model to do that. Well, at least from the equation, the idea is to adapt this part of the likelihood, or this part to the likelihood, to the specificities of your event history. And this is something that we did in different contexts, from using latent classes or shared random effect models. But this is the same for the repeated biomarkers. I mean, it's very rare that you only have one repeated biomarker of interest. This is the case with PSA, but that's quite a very specific example. Usually, you will think of different repeated biomarkers to describe the progression of your disease. And that can be, for example, when you have the tumor size and the PSA, you could be interested in that, or any blood marker and toxicity in a clinical trials, or with quality of life, that could be several scales of patient-reported outcomes, etc., etc. And the classical joint models do not handle that, so we need to extend them. And this is what I want to propose today with you, with a motivation in neurodegenerative diseases, with a very rare neurodegenerative disease, which is called the multi-system atrophy. This disease, the MSA, is characterized by an abnormal accumulation of alpha-synuclein protein in the brain. So the same protein as in Parkinson, but it does not go into the same brain cells as in Parkinson. The problem with this disease is that, well, it has a very, very poor prognosis. The median survival time is about 4 years after the diagnosis. And we know basically nothing about this disease. Very little knowledge on its etiology, its natural history, its progression, and no treatment. So there are many, many things to do with that. And the joint modeling approach is a way is an interesting tool to explore this disease. The multi-system atrophy is characterized, its progression can be characterized by different dimensions. We can think of a degradation of the function and the motor function of the patient over time. We might have a problem of blood pressure. And we also have a problem of dysautonomia, which is characterized usually by a problem of orthostatic hypotension. When someone stands up, we usually have a small loss of blood pressure, but in this disease, the loss of blood pressure becomes very, very pathologic. So basically, the type of data that we have for individuals who have this disease. So here I give you two examples with patient 1 and patient 2. We might have 6 biomarkers of interest. So 2 biomarkers that measure the function, 2 biomarkers that measure the decubitus blood pressure, so the diastolic and the systolic, and 2 biomarkers which measure the decrease in blood pressure when we stand up, so the orthostatic, I will call that the orthostatic blood pressure, with also the diastolic and the systolic blood pressure. So what you can see in these individual trajectories is that, well, the trajectory seems a little bit different between those two patients, but also you see that the data, they are not collected from the beginning. Well, when you are interested in the natural history of a disease, you want to begin your time zero should be the beginning of the disease, the onset of the disease. The problem with this type of disease and more generally neurodegenerative diseases is that the diagnosis might be done quite later. Sometime later. Here it's made 2 years after the beginning of the first symptoms, and here 6 years after that. Yet the first symptoms of MSA are quite specific. So basically you should not miss them if we ask you about those. So we have a quite clear assessment on when the onset of the disease was. The problem is just that those people are diagnosed here or here, and so we don't have the data before. This will, the setup of that will be a delayed entry that we will need to take into account in our modeling framework. And the other problem is that those individuals, those patients will die after a certain amount of time, and we want to take that also into account. So basically the framework for this modeling is that we have 6 biomarkers that evolve over time and the time to death. So we want to define a joint model with 6 biomarkers and a time to death. Why do we want to do a joint model? Well, that can be to address different research questions. We could be interested in looking at the clinical progression, describing the clinical progression and its determinants. So taking into account the fact that all those progression in function, in blood pressure are truncated by the informative death. And we could be interested in assessing how the clinical progression, so how those biomarkers will impact the risk of death. For that, I would recommend to use a shared random effect model for multivariate repeated biomarkers, which will quantify such things. But in neurodegenerative disease, we also, and in MSA in particular, we also have highly suspect an heterogeneity in the progressions. We highly suspect some subphenotypes of diseases. And so we want to explore that. And if we want to explore such a heterogeneity, it seems natural to use a joint latent class model instead of a shared random effect model. And finally, another type of question we could be interested in is to provide some individual predictions of the risk of dying, given the history of the biomarkers we had so far. And for that context, both approaches could be used. So in the remaining of the presentation, I want to show you an example of joint latent class model, and if I have time, an example of shared random effect model for that purpose. So if I want to extend the joint latent class model to take into account the multivariate repeated biomarkers, well, this is very easy. This is the exact same slide as previously, where I had only one biomarker. Well, the only change when I have multiple biomarkers is just that I will have a linear mixed model now for each biomarker. That's all. And so I just have, instead of having one linear mixed model specific to each latent class, I will have capital K linear mixed models with parameters that will be different from one biomarker to the other. If I want to estimate that, I told you that the estimation was done for a number of latent classes G, and then I can use the maximum likelihood. So compared to earlier, the only difference is that my contribution to the likelihood now includes the conditional density of all my biomarkers here, conditional to the latent class. I can use, so to do that, we have to optimize numerically this likelihood to obtain the maximum likelihood, and we use for that a Markov-Levenberg algorithm with very strict convergence criteria that we developed and made available in R very recently. And to take into account the problem of multimodality, we use a grid search. So we run the program from random initial values, many different random initial values, and we select the maximum, the global maximum that we obtain on all those random initial values. This is implemented in LCMM with function MultJLCM. Actually, this is not what I did. So this is the joint latent class for multivariate biomarkers. But the problem is that there are additional problems in neurodegenerative diseases. When I introduced you about this pathology, I told you that we had a problem of function, we had a problem of blood pressure, and we had a problem of orthostatic blood pressure. So basically, we don't have 6 biomarkers of interest, but we have 3 dimensions of interest. And those dimensions have each one 2 biomarkers that measure them. So we need to take this structure, this additional structure into account, and this can be done by defining the linear mixed model to describe the dimensions, but not at the biomarker level, but at the intermediate latent dimension level. This is done by a linear mixed model in which we don't have any error of measurement because those latent dimensions are no more observed. And then what we can do is to link those latent dimensions that I call lambda and d for 1, 2, 3 with the markers that are used to measure them. Well, to do that, it's quite straightforward to assume that a biomarker is just the latent dimension plus a certain error of measurement. So lambda plus epsilon. But if we have multiple biomarkers, then those biomarkers are maybe in different scales. And so we need to take that into account. And they might have different distribution. So to do that, well, we add to this equation of observation transformation, parameterized transformation, which will take into account the fact that those scales are different from one biomarker to the other with H, so it's the link function which is based on parameters, and you can have a link function which is linear, so it goes to the Gaussian framework with Gaussian biomarkers, or non-linear if you want to take into account non-Gaussian biomarkers. So that's the model that I wanted to show you today. So I estimated that on the cohort that we have the opportunity to analyze. So it's a cohort from the French National Reference Center for MSA, which is based in Bordeaux and Toulouse Hospital. So that's in the southwestern France, and I'm in Bordeaux. I live in Bordeaux. All the patients who were diagnosed with MSA between 2007 and 2019 were in France and who wanted to go to those reference centers were included in the cohort. And we have a follow-up every year. So now we have a very important, one of the most important cohorts for MSA in the world with 600 patients and measures every year. And among them, those 300 died during the follow-up. I will not describe specifically how I define this is a parametric model, so you have to define the type, the shape of trajectory, etc. We did that in preliminary analysis. I just wanted to show you the overall the type of results we had from that. So that's the type of result that you will always have to present when you have a latent class model. As you estimate your model for different numbers of latent classes, so here from 1 to 6, you need to select the optimal number of latent classes. And this is done usually using statistical criteria and other criteria if you want also. So that's the log likelihood that is associated. And when you want to obtain the model that best fits the data, then you will rely on the BIC to, with the lower the better, to have the best fit of your data. But in our context, we were interested also in looking at subphenotypes. So we wanted to have classes that could discriminate very well the data, very clearly define latent classes. And so the fit was not the only thing that we were interested. We were interested in the entropy, so the discriminative power of our model, to be able to really have a latent class structure that was interesting. And so that made us choose the 5 class model, even though the 6 class model gave a better fit. We did that according to BIC and entropy in a composite criterion, which is called ICL, with the lower the better. So here are the results, the main results of this model. So we obtained 5 latent classes here in each column, and the latent class 3 was about included half the people, and the latent class 1, 30% of the people. We had also 2 small latent classes of 9% and a very, very small latent class of 4%. I did not report here all the biomarkers, only one biomarker by dimension. And you have also the survival function. So what you can see here is that first, the largest class is characterized by a function. So that's the degradation of the motor and the function over time, with a degradation that is slower than in the other classes. So this class is different from the others based on this speed of degradation. Then if we look at the latent class 1 in black, well, the shape of degradation is the same. But actually, if you look at the blood pressure, you will see that it's very different from the one from latent class 2 and latent class 5. And if you look at the decrease, the trajectory of orthostatic blood pressure, it's quite stable over time, while it's very different and with a decrease of the problem over time. Here it's 0, a decrease of the problem over time for the latent class 4. So we can see how those classes differ the one from the other. If we look at the latent class in green in light blue, we don't see from the biomarkers a really big difference in the shape and the speed of degradation. But what we can see is a difference in survival here. Basically, this difference in survival seems to be linked to the time of diagnosis. So the length between the first symptoms and when the people were diagnosed, which is quite later here. You can see here the people are seen after at least 2 years, when here they are seen quite from the beginning of the first symptoms. So this type of results is what we wanted to have, to be able to summarize from complex longitudinal data, have a very a summary that was easy to understand. And this was to describe the disease, but also to be able to go a little bit further and to try to understand who were, why what were the characteristics of those subphenotypes, and why did we observe such different phenotypes of progression? So basically, to do that, we can try to associate those classes of progression with other clinical characteristics. How do we do that? We can rely on the posterior probability of class membership. Basically, from all the information we have on a subject, we can say whether the probability that it has to be in latent class 1, 2, 3, 4, and 5. And we can then assign him or her to the class to which he has the highest probability to belong. And so that's defined a class membership C at. If we want to look at to explain those latent classes, we can use some posterior regressions that will involve the classification, that can be either to explain external characteristics Z according to the class membership C, or to explain the class membership C according to those external characteristics Z. In both cases, the problem is that has to be done with C, and we don't know about C because this is a latent variable. What we know is about P at and C at, which are and this is different. We have an uncertainty if we use C at instead of C. We have an uncertainty in this and an error, a classification error in this latent class assignment. So to take into account this uncertainty that we have in this posterior classification, what we did is that we incorporated those posterior regression into the joint modeling program to directly internally take into account the uncertainty. And so we were able to look at the characteristics of each class in multinomial logistic regression. So basically the reference category was the latent class 3, and we looked at different characteristics at baseline. So you can see that we don't have so many characteristics at baseline to explain them, and this is not really interesting here. to go further into details. What was more interesting, I think, was to use those latent classes to explore new assumptions and new directions of research regarding biomarkers, new biomarkers developed in the area. And I give you here an example with MRI data, so different regional volumes of the brain. And we were able to look at those volumes according to the latent class while taking into account the uncertainty. This is a very exploratory analysis with only 86 people who had those MRI. And what we can see is that, for example, if we compare with latent class 3, we can see some differences for the 2 and 5 regarding the pont. We can see some differences with latent class 1 for the putamen. Those two regional regions of the brain are very central in MSA, and we can also see some slight difference in the cerebellum white matter. The cerebellum is also a region of main interest in this disease. This is only for illustrative purpose. It was to show you what we can do with that. So I wanted with this application to show you that the latent class approach could be an interesting tool to separate, to make an overall separation of the patient with different subphenotypes. And this is very useful, particularly useful to explore complex settings when we have multiple processes and we need to summarize that in some way. So we use that to identify the subphenotypes, to describe them, but also to investigate, so MRI, as I showed you, but also fluid biomarkers that could be targets for therapeutic research, and that could also be used for individual dynamic prediction purpose if we wanted. But one thing I want to insist on is the fact that this approach is clearly descriptive. There is no clear assessment of the association between each dimension and the survival. I only describe the data and summarize the data. And the second thing is that I don't intend to take into account precisely and perfectly the correlation structure with the endpoint. I only have a few latent classes to take into account the association I have between different processes. But those latent classes offer a very nice tool to be able to summarize that quite easily and quite easily. If I want to go further into such idea of assessment of the association with between the dimension and the survival, then I need other tools. And this is the last part of the talk that I wanted to give you, where we can describe the clinical progression and assess how the clinical progression impacts the death using a shared random effect model. So for now, we have described the 3 dimensions that evolve over time with the time to event using a latent class structure. But if we want to do exactly the same thing with a shared random effect structure, then the model is like that. We have the random effects from each dimension that will be associated with the time to event. If we want to estimate that, then we can write down the likelihood. And what you see is that you have a very nice integral here of dimension d times p. P is the number of random effects per dimension, d is the number of dimensions. So if you have 3 dimensions, 3 random effects, you have an integral of dimension 9. And this is clearly not feasible to do that, well, accurately at least. So that was a problem that we had for many years with the extensions of the shared random effects model with for multivariate outcomes, and there have been some recent proposals using alternative methods to deal with this numerical integration, and I wanted to share with you one of them, which is simply to make it disappear. So the idea here is to say that when you do this type of model, what you want to do actually is to assume that your dimensions impact are associated directly with the time to event. The random effects are a way to model that, but actually that's what you want to assume as an association. And if you do that, well, you could go one step further and say that if those dimensions, all those dimensions impact the time to death, maybe actually there is a degradation process underlying death, which is characterized by all those dimensions. And then the time to death is just a manifestation of this degradation, this overall degradation process. So basically, we would have a degradation process over time. And once you are above a certain threshold, then it means that you have the clinical event. That could be a diagnosis. In our case, it would be death. So to do that, well, the idea is the same to deal with each of the dimensions. It's exactly the same as before. You have a mixed model to describe the trajectory of your dimension over time, and you have a nonlinear link function to link your latent dimension with the outcomes. That does not change. What will change is the way we associate those dimensions with the degradation process and the time to death. To do that, what we can do is to define the degradation process, so delta E, as a linear combination of all my degradations, all my latent dimensions. So that will be how the first dimension contributes to the overall global degradation process, how the dimension D contributes to the degradation process, etc., etc. And then what I say is that this degradation process plus an error, when it's above a certain threshold that I will estimate and can depend on time, then I observe that the event is 1. So the person has the event, has already the event. So that's the way we can define a shared random effect model as an alternative to the proportional hazard model that we are used to in joint models. How we can estimate that? Well, the idea is to use the maximum likelihood estimation. So we have the joint likelihood of the event and the biomarkers. And so we have this integral over the latent dimensions. What is shared here as the latent, all those latent dimensions. So my integral is over the latent dimensions. I rewrite that to make f of y not into the integral. And then what is very, very nice with this approach is that this is a multivariate normal density function, and this is a cumulative probability function of a multivariate normal. So I think I gave you all the ideas here. It's just that we get rid of this integral by using this definition of the latent degradation process for the event that is based on the normal framework, and so we can use those properties. Okay, so we wanted to apply this methodology to the MSA to understand what dimension mostly correlated with death. So to understand the disease progression, what was important in the disease progression, and to make it possible to predict at an individual level the risk of death. We use for that the same data, and I will just go to the results. So this is not really, well, I hope you will understand that quite easily. So here we compare different models. A first one where we consider that the overall global degradation process was only defined from the functional level. So only one dimension defined this overall degradation process, only one. And then 2 of them, and then 3 of them. And we compare those models, but we were not able to compare them basically on a global criterion because they don't use the same type of information for the longitudinal part. So basically what we did is that we compared them according to information criterion that were based only on the survival part. And so this is what is reported here. So we have the contribution of the function here when we only take that into account, decubitus blood pressure and orthostatic blood pressure. When we take into account 2 of them, 2 of them, 2 of them, and 3 of them. And basically here are 2 information criterion for the criteria for the survival, the conditional AIC and the conditional the universal approximated cross-validation criterion that we developed, and here for both the lower the better. So basically we found that this model gave the better fit of the survival data, and that was based on the function and the decrease in blood pressure, not the decubitus blood pressure. And we use that to be able to make some individual dynamic predictions. So basically, the dynamic individual prediction is consists in looking at a certain time that we call landmark, and to look at the risk of having the event, for us the death, after a certain amount of time from there, according to the history of the biomarker I have for my individual up to this landmark time. And so we use that on this model based on the 2 dimensions. So 4 different biomarkers, 2 dimension, the orthostatic blood pressure here and the function here. And so for an individual, we were able to predict the risk of death from this information, and we were able to update that when we had more information, etc., as it is usually done in the dynamic individual prediction context. We found that we compared that according to Brier score and AUC. I will not describe that, but it just says that it gave interesting, well, it was better than alternatives. Okay, so I will conclude here. I'm still online, so that's very good. So I wanted to show you today how the joint models, even if this is a methodology that is very has been developed for quite a long time, still needs to be adapted to the data complexity, because we don't usually have only one biomarker, one time to event, etc. And I wanted to stress on that there exist different types of joint models, and that you should not systematically use one or the other. It completely depends on the question you have. If you want to make some description, then maybe the joint latent class model would be best. If you want to quantify association, maybe the shared random effect model will be best. And in the 2 types of approaches, they rely on the same principle, and so the same possible extensions are possible in those 2 frameworks. So there are many ways to go further into this methodology. I'm pretty sure you already see some of them. So I will just go to the acknowledgement. I wanted to thank my co-workers, and in particular Viviane, Philippe, and Tiffany Sonnet. They did most of the programming and analysis stuff that you saw here, and my colleagues, experts in MSA. And here I give you some references and the programs if you want to try them. So thank you very much for your attention.